Welcome, my dear learners, for this course on heat transfer. In this module 3, we are discussing on numerical analysis in heat transfer and radiation heat transfer. So far, we have completed our discussion on numerical analysis in heat transfer. Continuing our discussion from today's lecture, we are starting a new topic, that is thermal radiation. So let us discuss some important definitions which we are going to use in the analysis of thermal radiation in today's lecture, and also let us discuss the laws of radiation. Moving ahead, coming for radiation, the basis for defining radiation is Maxwell's theorem. According to Maxwell's theory, every body possessing temperature greater than the absolute zero temperature emits radiation in the form of electromagnetic waves. I repeat once again, every body possessing temperature above absolute zero temperature emits radiation in the form of electromagnetic waves. The basis for defining radiation is Maxwell's theory. And one more important note regarding radiation is that for radiation mode of heat transfer, no material medium is required for propagation. Unlike conduction and convection, for radiation, no material medium is required for propagation of heat. And moreover, the radiation heat transfer is much higher or much more effective in vacuum. In vacuum, the electromagnetic waves even travels nearly as the speed of light. So therefore, in vacuum, if I want to determine the wavelength of electromagnetic waves, that is thermal radiation, I can use the basic equation which we all know, that is speed of light is equal to frequency into wavelength. So therefore, wavelength can be determined by using the equation speed of light divided by frequency, where speed of light is given by 3 into 10 to the power of 8 meters per second, and F is frequency in hertz or in cycles per second. And also, this radiation is defined by Maxwell's Planck's theory as the radiation is also emitted. The energy emitted by radiation will be in the form of tiny packets of energy called photons. So from Maxwell's Planck's theory, we can also have the equation for energy emitted by radiation is given by h times lambda, where h is Planck's constant. So this is from Maxwell's Planck theory. So the basis for explaining radiation is Maxwell's theory. Next topic is black body. So black body is an idealization like Carnot engine. Black body concept is used as a reference for analysis of real bodies. Now coming for black body is one which absorbs all the radiation incident on it. Since it absorbs all the radiations incident on it, for equilibrium it should emit all the energy what it is absorbed. So therefore, a black body is a perfect absorber as well as it is a perfect emitter. So therefore, a black body is a perfect absorber as well as it is a perfect emitter. A good example for black body is that ice is also a good example for black body because it absorbs all the radiation which is incident on it. So therefore, ice is also a good example for black body, and also platinum black is also an example for black body. Even though their emissivity is not equal to 1, but it is nearly equal to 1. The ice possesses an emissivity of 0.97 to 0.98. Hence, ice is also treated as black body. Next, coming for emissive power. Emissive power of a black body is defined as amount of radiation emitted per unit area per unit time. So therefore, emissive power of a black body is explained with the help of Stephen's law. So emissive power of a black body is directly proportional to 4th power of its absolute temperature. The amount of energy emitted per unit area per unit time is termed as emissive power of a black body. For a black body, the emissive power is directly proportional to fourth power of its absolute temperature from Stephens-Boltzmann's law. I'll take up Stephens-Boltzmann's law in detail when I take laws of radiation. So emissive power is nothing but heat flux. Next, moving for emissivity. Emissivity is defined as emissive power of a real body to the emissive power of a black body. I already said that the emissive power is maximum for black body. So therefore, emissivity is always less than unity. Emissivity of any body varies from 0 to 1. Whereas emissivity is defined as the ratio of emissive power of real body to the emissive power of black body. Next, now to explain absorptivity, reflectivity and transmittivity, if I consider radiation incident on a surface, let us consider a surface like this. I have radiation incident on it. Let the radiation incident on it. When a radiation is incident on a surface, three things can happen. This radiation can be absorbed, this radiation can be reflected, and this radiation can be transmitted. That is, if I consider the incident radiation, three things can happen. One is it can be reflected, it can be absorbed, it can be transmitted. So if the incident radiation is termed as Q and the amount of energy reflected is termed as QR, let me define it as QA, amount of energy absorbed as QA and amount of energy transmitted as QT, then the incident radiation Q should be equal to amount of energy absorbed plus amount of energy reflected plus amount of energy transmitted. So if I divide throughout by Q, I get 1 is equal to QA by Q plus QR by Q plus QT by Q. So therefore, this is nothing but QA by Q is nothing but absorptivity, which is defined as alpha. QR by Q is defined as reflexivity, which is defined by symbol beta, and QT by Q is defined by gamma, which is nothing but transmittivity. So therefore, absorptivity is defined as fraction of incident radiation that is absorbed by the surface. Fraction of incident radiation that is absorbed by the surface. Whereas reflectivity is defined as fraction of incident radiation that is reflected from the surface. And coming for transmittivity, it is defined as fraction of incident radiation that is transmitted from the surface. So this is a very important note to be known for you people. So if I consider an radiation incident on a surface, three things can happen, from which I can define absorptivity, reflectivity and transmittivity. The fraction of incident ray that is reflected is termed as reflexivity. The fraction of incident radiation that is absorbed by the surface is termed as absorptivity. The fraction of incident radiation that is transmitted can be termed as transmittivity. The sum of these three should be equal to unity. So this is about the concept of emissivity, absorptivity, reflectivity and transmittivity. Next, moving for the concept of white body. A body is considered to be a white body if it reflects all the radiation that is incident on it. So therefore, for an white body, it reflects all the radiation incident on it. So therefore, beta is equal to 1 and alpha and gamma is equal to 0. Alpha and gamma is equal to 0. Next, coming for The next one, that is gray body. If the emissivity of an non-black surface is constant for all temperatures for the entire given wavelength range, then it is termed as gray body. If the emissivity of a non-black body is constant for all temperatures throughout for all ranges of wavelength, then it is termed as gray body. All real bodies are approximated as gray bodies, for which we treat the emissivity is constant for all temperatures for the entire given range of wavelength. So gray body is very important for us because we approximate all the real bodies as gray body. Next, moving for opaque body. So here I can state emissivity is constant for all temperatures and entire range of wavelength. For gray body. Next concept is opaque body. So if I consider opaque body, the body is said to be opaque if it not transmit any of the radiation incident on it. So for an opaque body, the transmittivity is 0. For opaque bodies, transmittivity is 0. So therefore, absorptivity plus reflexivity should be equal to 1. Next is transparent body. A body is said to be transparent if it transmits all the amount of radiation incident on it. So therefore, for transparent body, since it transmits all the radiation incident on it, gamma is equal to 1. So therefore, alpha and beta should be equal to 0. That is, absorptivity and reflectivity should be equal to 0. So this is about the concept of various bodies. That is black body, white body, gray body, and opaque body, and also transparent body. Next, moving for intensity of radiation. That is, if I want to define intensity of radiation, let me consider a surface like this. Let us consider an area DAP, an elemental area here, which is collector, and this is considered to be an emitter. Then I can define this as normal, and this angle I will define it as theta, and this angle I will take it as theta. And this projected angle I will take it as d phi. Now, coming for intensity of radiation, the intensity of radiation I is defined as amount of energy emitted per unit projected area normal to the direction of radiation per unit solid angle. I repeat once again, intensity of radiation is defined as the amount of energy radiated from a surface per unit projected area normal to the direction of radiation. So therefore, the amount of energy radiated, let me take it as dq per unit area projected normal to the direction of radiation. I am projecting the area in the normal direction, so therefore I should take it as cos theta. So therefore I am taking it as cos theta per unit solid angle. So therefore I should multiply this by d omega, where d omega is solid angle. So this is the definition for intensity of radiation. Intensity of radiation is defined as the amount of energy radiated from a surface per unit projected area normal to the direction of radiation per unit solid angle. Now, what do you mean by solid angle? So if I consider a plane angle, that is, if I consider an angle like this, then this angle is termed as plane angle. So if I take this as S and this as R, the plane angle theta is defined as S is equal to R theta. So therefore, theta is equal to S by R. The unit is radian. Whereas solid angle is defined as, if I consider a conical surface like this and project it to the center. So here I will get an angle at the center C like this, which is termed as solid angle d omega. So if I consider this as area dA and radius as r, so then I can define the solid angle d omega as dA by r square. The unit of solid angle is steradian. The unit of solid angle is steradian. So this is how we can explain the solid angle. That is, from the center, if I connect the surfaces, I will get a three-dimensional angle at the center, which is termed as solid angle. The equation for solid angle is dA by r square and the unit is steradian, whereas this is plane angle. For plane angle, we consider the surface depth as unit. We have unit depth, which is 2 dimension. Whereas here, if I consider a cone, it is 3 dimension for us. So connecting from the surface to the center, the angle substituted to the center C will be called as solid angle, which is defined by dA by r square and its unit is steradian. Next, moving ahead for irradiation. Next, coming for next topic, that is irradiation. So now to explain irradiation, let me consider a surface on which the radiation is incident on the surface. So this surface can also emit radiation, and also the surface can reflect. Now, coming for irradiation, irradiation is defined as amount of radiation that is incident on a surface per unit area per unit time. Amount of radiation incident on a surface per unit area per unit time is termed as irradiation, which is denoted by G. So this is the amount of radiation incident on a surface measured per unit area per unit time, which is defined as irradiation. Next, coming for radiosity. Radiosity is defined as the amount of radiation leaving the surface per unit area per unit time. The difference between radiosity and irradiation is the amount of radiation incident on a surface per unit area per unit time, whereas radiosity is the amount of radiation leaving the surface per unit area per unit time. So if I consider the radiosity J, if I consider the radiosity J, if you observe the amount of radiation leaving the surface per unit area per unit time is because of emission and reflection. So this reflection is some part of the amount of radiation striking the surface. So therefore, it is reflexivity times the irradiation G. Hope you understood. Because all the incident radiation will not be reflected. So therefore, only part of the incident radiation will be reflected. So that part of the incident radiation that is reflected is termed as reflexivity. So therefore, reflexivity times the irradiation will gives us what is the amount of reflected radiation, and we are emission. So therefore, we know that beta is nothing but reflectivity, where G is irradiation. Now, for black body, if I consider, black body is one which absorbs all the radiation incident on it. So therefore, reflectivity for a black body is 0. So therefore, radiosity J for a black body is equal to emissive power. So this is what we can conclude for a black body. And this is the relationship between radiosity and irradiation. So thereby we have completed the important definitions which one should know in thermal radiation analysis. Next, let us start discussing loss of radiation. Next, coming for loss of radiation. So first one is Stephens-Boltzmann's law. Stephens-Boltzmann's law. Stephens-Boltzmann's law of radiation states that the emissive power of a black body is directly proportional to fourth power of its absolute temperature. So therefore, if I take the emissive power of a black body, which will be proportional to fourth power of its absolute temperature, so therefore, emissive power of a black body is equal to proportionality constant sigma times T to the power of 4, where sigma is nothing but Stephens-Boltzmann's constant, which is given by 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. So this is Stephens-Boltzmann's constant, which we can easily remember is 5678. So you should know where to put the point and the negative sign. Now, so therefore, the amount of energy radiated can be determined as Q is equal to, we know that this is flux. So therefore, for a black body, multiply by area. So sigma A T to the power of 4. Now, for non-black surfaces, I can write the amount of radiation is given by emissivity times sigma A T to the power of 4 watts. So this is about Stephens-Boltzmann's law of radiation. Next, second one is Kirchhoff's law. Kirchhoff's law. Coming for Kirchhoff's law of radiation. Kirchhoff's law of radiation states that when a body is in thermal equilibrium with the surroundings, then emissivity is equal to absorptivity. So emissivity epsilon is equal to absorptivity, that is alpha. Emissivity is equal to absorptivity when a body attains thermal equilibrium with surrounding. This is about Kirchhoff's law of radiation. When a body attains thermal equilibrium with surrounding, then emissivity will be equal to absorptivity. Next, moving for the third one. Third one is Planck's law of radiation. Coming for Planck's law of radiation, Planck has been determined the spectral distribution for radiation at different wavelengths, and he has given the equation for emissive power of a black body, which is given by constant C1 times lambda to the power of minus 5 divided by e to the power of constant C2 by lambda t minus 1. C2 by lambda t minus 1. So E stands for exponential. So this is the equation given by Planck for spectral distribution, what he has determined. So from this equation, he has specified the emissive power of a black body, and he has plotted the emissive power EB versus various wavelength for the spectral distribution at various temperatures. Let us take this as T is equal to 1000 Kelvin. Let us take T is equal to 2000 Kelvin, and let us take T is equal to 3000 Kelvin. And from this, the Planck observed two important points. That is, the first one, emissive power increases with increase in temperature. Emissive power increases with increase in temperature. Emissive power increases with increase in temperature, and also the peak spectral emissive power spectral emissive power shift towards smaller wavelength at higher temperature. So this is about Planck's law of radiation. So Planck has determined the equation for emissive power, and he has given the spectral distribution. From the spectral distribution, he has observed that the emissive power increases with increasing temperature, and also the peak spectral emissive power will shift towards the smaller wavelength at higher temperature. As you increase the temperature, the peak value of emissive power will shift towards the smaller wavelength. So this is what he has stated. So this is about Planck's law. Next, fourth one is Wein's displacement law. Wein's displacement law. This Wein's displacement law is based on Planck's law. So Wein's displacement law states that the product of wavelength corresponds to maximum emissive power, and the absolute temperature is equal to constant. This is not maximum wavelength. Understand properly, the wavelength corresponds to maximum emissive power. So wavelength corresponds to maximum emissive power. Wavelength corresponds to maximum emissive power. Wavelength corresponds to maximum emissive power, and the multiplication of absolute temperature will be constant. If I want to prove this, I should differentiate this emissive power of a black body with respect to lambda and equate it to 0. And if I solve, I'll get lambda max plus T. Lambda max into T will be equal to constant. That is, wavelength corresponds to maximum emissive power into the absolute temperature is equal to constant. This is what Wein's displacement law states. The product of wavelength corresponds to maximum emissive power and the absolute temperature will be constant, and this constant value is nothing but 2900 micron meter Kelvin. Micron meter stands for 10 to the power of minus 6. 2900 into 10 to the power of minus 6 meter Kelvin is the value of constant. So this is about Wein's displacement law. Next, I want to discuss the last one, that is Lamberts cosine rule, and later I will prove the relationship between emissive power of black body and intensity of radiation. Now, in order to explain Lamberts cosine rule, let us consider the same diagram which I have drawn to explain intensity of radiation. So, I have redrawn the same diagram which I have drawn to explain intensity of radiation. Now, from the Lamberts cosine rule, which states that the diffuse surfaces emits radiation such a way that the energy radiated in any perpendicular direction is directly proportional to cosine of the angle between the direction under consideration and the normal to the surface. I repeat, Lamberts cosine rule states that the diffuse surfaces emits radiation in such a way that the amount of energy radiated in any perpendicular direction is directly proportional to cosine of the angle between the direction under consideration and the normal to the surface. Let us consider the surface dA as diffuse surface. Then the radiation emitted in any perpendicular direction, let us consider the direction as OP, is proportional to the cosine of the angle between the direction under consideration and the normal to the surface. Let us consider ON as the normal. Now, if the amount of energy radiated in the normal direction is dN, energy radiated in normal direction let us consider dq theta as the energy emitted in direction OP. This as energy emitted in the normal direction. So from Lamberts cosine rule, we can write that dq theta is equal to cosine of the angle. Cosine of the angle between the direction under consideration and the normal. So therefore, it is cos theta times dq in the normal direction. So this is what Lamberts cosine rule states. The diffuse surface emits radiation in such a way that the amount of energy emitted is directly proportional to the cosine of the angle between the direction under consideration and normal to the surface. This is about Lamberts cosine rule. Now I am moving ahead to the final topic of today's lecture, that is to prove relationship between emissive power and intensity of radiation. Relationship between emissive power EB and intensity of radiation. Let us consider the same diagram. Let me call this as figure A. So from figure A, let this surface be the emitter and this surface be the collector. Now, what is the area of the collector? Area of collector. What is the area of collector? So, area of collector is a rectangle. I can write it as length AB into length BC. Now, length AB is already known to us. That is, S is equal to R theta. So, therefore, AB will become R times theta is d theta. Now I want to know this length BC, so therefore I is projected into the base. So this is also equal to length BC. This BC length I have projected here. This is also equal to BC, and this length will become the vertical component of radius. So this is the radius R. So therefore this length will become the vertical component of radius which is projected here. So that is nothing but R sin theta. So therefore this length is equal to how much? R sin theta. So this length is R sin theta. So therefore S is equal to R theta. Again, if I apply, length BC will become R sin theta d phi. Length BC will become R sin theta d phi. Hope you clearly understood how I calculated the area of collector. I have projected length BC to the base and I have calculated. So this is the variation of angle phi, which is 360 degree, that is 2 pi, whereas theta varies from 0 to 90. Next, we have calculated the area of collector. Now, what is the value of solid angle? Solid angle d omega, which is already known to us, which is dAc by r square. So therefore, we know area of collector r d theta will become r square sin theta d theta d phi. So r square and r square will get cancelled. So therefore, I left out with sin theta d theta d phi is the value of solid angle d omega. Now, from the definition of intensity of radiation, we know that intensity of radiation is defined as the amount of radiation emitted from a surface per unit area projected normal to the direction per unit solid angle. So therefore, intensity of radiation is defined as amount of energy emitted per unit area projected normal to the direction dA cos theta per unit solid angle d omega. So from the definition of intensity of radiation, we already seen this equation. So I am recalling this equation from the definition of intensity of radiation. So therefore, dq, the amount of energy emitted from the surface dA, will become intensity of radiation into area dA into cos theta into d omega is sin theta d theta d phi. So therefore, total energy emitted from the surface will be, integral is from 0 to q dq, which is equal to intensity of radiation dA. Now theta varies from 0 to pi by 2, 90 degrees. We have sin theta cos theta d theta into phi varies from 0 to 2 pi d phi. So therefore, if I solve, I will get intensity of radiation into dA. So this I should write it as 0 to pi by 2 sin 2 theta by 2, because sin 2 theta is sin theta, 2 sin theta cos theta. Therefore, I can write as sin 2 theta by 2 into, if I integrate, I will get phi, which varies from 0 to 2 pi. So therefore, if I integrate and solve, I will get the equation as intensity of radiation times dA into by 2 into 2 pi into integral of sin 2 theta is minus cos 2 theta by unit varies from 0 to pi by 2. So therefore, if I substitute and solve, so cos 180 is minus 1. So therefore, I'll get Q is equal to intensity of radiation into dA. 2 will get cancelled into pi. I will take this 2 outside. So therefore, it will be 1 by 2 times. If I substitute pi by 2, 2 will get cancelled. So I will take it as minus 1 by 2 outside. I have cos 2 theta, pi by 2 and 0. So cos pi is minus 1 minus cos 0 is 1. So therefore, Q is equal to intensity times dA into pi. This is what I got. Now, from Boltzmann's law of radiation, you know that Q for a black body is equal to sigma dA e to the power of 4. So therefore, if I equate these two for amount of energy emitted from the surface, I will get intensity of radiation times dA into pi is equal to sigma dA t to the power of 4. So sigma dA will get cancelled. I left out with intensity of radiation into pi is equal to sigma t to the power of 4. So we know that sigma t to the power of 4 is nothing but emissive power, because emissive power of a black body is defined as the amount of energy emitted per unit area per unit time, which is directly proportional to 4th power of its absolute temperature. So therefore, emissive power of a black body Eb is equal to sigma t to the power of 4. This we already know. So hence I can write intensity times pi is equal to emissive power of a black body. So therefore, emissive power Eb is pi times the intensity of radiation. So we have proved that emissive power of a black body is pi times the intensity of radiation. So this is a relationship between emissive power of black body and intensity of radiation. Now, with this very brief introduction to thermal radiation, in our next lecture, I will take up a very important topic, that is U factor. That's all from this lecture. Thank you all.